Before I start on today's, I want to tell you one correction in the last numerical problem that we did. Actually, it's a what you call a copying mistake here. While explaining this graph, I have told like it is the total voltage is from dropping from 200 to minus 800, and then it is dropping further to minus 1000. But when you observe this equation, it was not found to be happening here. So actually the mistake is happened while uh, we were doing this. So here up to here I have written that it is equal to 20 into 10 power 4. Okay. Then while copying it down here, I dropped that 4 here. So we were not able to reason out. So don't forget this 4 here. Because here no, the current equation that we have written is the slope, that is minus 10 by 1 into 10 power 3. So when you take this 10 power 3 to the numerator, so it will be 1 into 10 power 4. Okay, so this 10 minus 10 into 10 power 3, so that is 1 into 10 power 4 t. Okay. So we have all the calculation that we have done is correct only, but only thing here I forgot to write it as 10 power 4, and that 10 power 4 should be reflected here, so that when you multiply with 200 also, that 10 power 4 will be there. Okay, so there is no difference in the voltage across the inductor. Then when you add it up also, it will be minus 800, the voltage across the resistor. So VRL is the total voltage across the resistor as well as the inductor. So VRL is equal to VR plus VL, and VR we have written as 200 minus 20 into 10 power 4, and VL is minus 1 into 10 power 4. Okay, and when you multiply it with 1000 into 10 power 3, so it will be minus 1000 volt. Okay, so when you add it up, this minus 1000 plus this 200 will be minus 800, which is coming here, and this minus 20 into 10 power 4 has to be written like that, so that there won't be any confusion when you look at this graph. Okay, now you will be able to reason out what is happening here. So up to t less than 0 second, it will be the voltage, the total voltage across the series RL will be equal to 200. Then at t greater than 0 but less than 1 millisecond, it is taking the shape of minus 800 minus 20 into 10 power 4 t. Okay, so at t is equal to 0, this term will vanish. The 20 into 10 power 4 term will vanish, so that you will have only minus 800. So that is seen here, as you can see here, it is minus 800. Then the other boundary limit is when t is equal to 1 into 10 power 3. So at that time you will have minus 800 minus 20 into 10 power 4 into, instead of t you have to substitute for 1 into 10 power minus 3. Okay, so that will be equal to minus 800 minus 200. Okay, so here you will have 200, so that will be equal to minus 1000. So that is where this voltage is dropping to minus 1000 volt at t is equal to 1 millisecond. Okay, so you will be able to justify this graph also. Okay, so I hope that there is no doubts in the previous classes. If you have any doubt in any of the numerical problem that you are trying from your end, you can ask me. We'll have another class to explain that if you are stuck in at any stage. Okay, so today's topic is on Laplace transform. Okay, so have you undergone any course on Laplace transform before? Maybe in your engineering mathematics, you would have undergone a course in that. Second is I don't know whether you have undergone any course.
Yes,
Third
sir,
year,
in mathematics
Yes,
only.
yes.
okay, second year also. Okay, very good.
Yes.
So it will be a quick revision only because you already know what is the transformation, what it is doing. So can anybody tell me why we are doing Laplacian transform? Why are we doing Laplace transform? Because we study various methods. So when you study various methods, you should be able to tell me why we are studying. While I was talking on the matrix method, I told you what is why we are using matrices, because we already know have other methods. But why are we going for matrix method? Because of the computation. It's easy to make algorithms using that matrices. Okay. Similarly, why are we studying about Laplace transform? Why are we doing the Laplace transform? What simplification it is going to bring to us? So, in mathematics, you must have studied only that there is a transformation called the Laplace transform, but nobody must have cared to ask why we are doing. Teacher or sir who is teaching the mathematics subjects, you should have asked them why are you doing this. So they would have explained the relevance for this. But in this course, while we do study about this, then you will be able to appreciate the importance of this Laplacian transform. So we will be starting with some basics of these things. So when you have more complicated equations, partial differential, differential, be able to appreciate its real importance. So how much it simplifies our calculations. Okay. So they are going to simplify our solution of differential equations, this Laplacian transform. So what we are doing is we are transforming. So we have got a certain differential equations. For example, whenever we say what is the voltage across a capacitor, so we will have voltage across a capacitor VC is equal to 1 by C integral I dt, or what is the voltage across an inductor, in which we will have a differential equation. So that is equal to L di t by dt. So we'll have a lot of different derivatives and integrals coming there. Okay, so it is going to make our calculations in the time domain more complicated. So every time we have to do integration. For example, I have shown you how to find the average value, etc. So integration is very time consuming process. Similarly, solution of differential equation is also very time consuming. So what we do here is that we transform this instead of the time domain, that is in the time axis, we do some transformation. Uh, so that the entire quantity is whatever we are interested in. The domain is uh, the domain in which we are trying to solve the equation is transformed to a complex frequency domain, which is otherwise called as the Laplacian domain. So in that domain, so it is like we are changing the coordinates. Like for example, if we can do a, if you have undergone a course in electromagnetic theory, you would have known it is not easier to do all interpretations or calculations in the this rectangular coordinate system, because they are because of their technical, or because of their technical, or because of their geometry. So it is very difficult to do all these calculations. So what we do is we are transforming this. So we have got a certain differential equation. So we are transforming this one-sided Laplacian transform in which we are interested only in positive time intervals. We are not interested in what is the past events. Okay. So all the theory is written here. S is a complex domain which is represented by sigma plus j omega, where omega is the imagine complex axis. Then another thing is we once we convert if you look at this integral equation, then you may think like it is a very complicated process, because you have to find out the integral with respect to some function into you, like I have already said that you don't have to do any integration, but the thing is that we have certain standard transformation equations readily available, so that we don't have to always do this integration process each and every time. So we will see what are those standard transformation equations readily available. So we don't have to do all the integration every time. We have to only inspect our function and see and convert, take any of the correct transformation and apply it in our equation. So the task is very simple, even if you see that the integration looks very difficult. And after doing the linear transformation, linear simplification, so once we convert it to the Laplacian domain, our differential equation vanishes. These derivative terms will be converted to simple linear equations, which we can solve very easily, either simultaneously or by substitution or cross multiplication, etc. So after doing all those things, the we will in order to get back the original function in the time domain, we have something called as the inverse Laplacian transform. There also we have certain standard transformation equations readily available. So once we have the equations in the S domain is available, we can convert it to those equations in the time domain. So we don't have to do this integration again in order to convert it back to the time domain. If those equations are not meeting our requirements, then of course you can use this equation and integrate it along the complex axis in order to convert the uh, quantity that is available in the S domain back to our time domain equations. Okay, so that is the introduction on Laplace transform I can tell you. So you can refer any mathematical textbooks to study more on how it is done and how it is working, how we are transforming to a different domain. And like I said, there are certain test signals or signals that are already available, which we have studied. For example, E of t, which is the unit impulse function, sorry, unit step function. So its Laplace transformation is already uh, available. So you can also do that integration and find out what is the integral of that u of t into e power minus std. So ultimately, you will get the result as the Laplace transform of u of t is equal to 1 by s. So we need to only remember that the Laplace transform of a unit step function is equal to 1 by s. So whenever we have the signal, whenever we have an equation containing u of t, you can convert it to its Laplacian domain by just taking its by replacing it by 1 by s. For example, if you are having so what is u of t? U of t is just like 1. For example, you can have Laplace transform of 1. A DC voltage is equal to 1 by s itself. Similarly, you can have the Laplace transform of 10 times u of t is equal to 10 by s, like that. You can do the conversion very easily. You don't have to do the integration each and every time. Or in other words, I can say the Laplace transform of 10, if it is a what do you call a voltage, then you can convert it to 10 by s, like that. Okay, so that's explained here. So we have called the linearity property of Laplace transform, which allows us to multiply any function with a linear with a constant and then convert it to its Laplacian transform. Just replace the function with 1 by s, and you can multiply the constant as such, like this. Okay, so that is done here. Similarly, another function which we need in our network course is the exponential function, which we have already discussed elaborately in our previous classes. So we have e power minus at, which is an exponentially decaying function. So the Laplacian transform of a e power minus at is nothing but a by s plus a, where a can take any value. For example, I can have a is equal to 1, in which I can get the Laplacian transform of e power minus at is equal to 1 by s plus a. Similarly, the small a can also take different values. For example, I can write the Laplace transform of e power 2t is equal to 1 by s minus 2. Okay, so like that we can do the transformation process to any function. Then once you have the uh, final result in this form, you can also take the inverse Laplacian transform. So whenever you see a function of the form in the S domain, you can easily take the Laplace inverse Laplace of that function. That is L inverse, which is represented by L inverse of a by s plus a. You can readily write it in the time domain as a into e power minus at. Okay, so that is very easy. You don't have to do any integral to convert it to the Laplacian domain or coming back to the inverse Laplacian, that is the time domain. Okay, another very frequently used function is the sine function. So we can convert a sinusoidal signal in the time domain. So we can do a Laplace transform L of sine omega t. So it will be given as omega by s square plus omega square. Okay, where omega is the angular frequency. And similarly, you can find out the Laplace transform of a cos omega t cosine function also, which is given by s by s square plus omega square. Okay, now we will see. Okay, another frequently encountered term is the derivative function. For example, in the for in order to find the voltage across the inductor, I have told like it is equal to L di by dt. So we'll encounter these kind of derivatives in our solutions. For example, when we write the KVL equation, we'll encounter certain forms. In between, we'll have an inductor. Then what is the voltage dropped across the inductor? So we'll encounter these kind of expressions. So the Laplacian transform for such a function, that is Laplace transform of the derivative of the function in the time domain, that is d by dt of f of t, is equal to s into the Laplacian transform of that function, that is s into f of s minus the initial condition, which is represented by f of 0 plus. So this plus is indicating that we are interested only in the positive time region. Okay, we are not interested of what are the past events. That is t less than 0. That is not interested. So f of 0 is otherwise called as the initial condition. So in our network analysis, it is like we are having an inductor, and here already there is some current existing in this inductor. Let us call it as a current of I naught, I of 0 plus. So this current is already there in this inductor, and somehow, for example, I have a switch here, and this switch was connected to some voltage source, so that this I of 0 plus was flowing through this inductor. Now immediately I open this switch, so that this current is removed. So there will be some magnetic flux around this inductor, so that energy will be stored here. So this is an example for the initial condition. So when the new case, when t is equal to 0, I am trying to open the switch. That is, the current should automatically become equal to 0. Okay, so that should happen. But initially there is some current already flowing through the inductor. That is represented by this f of 0 plus, the initial condition. Okay, or I can add a more higher current to this across this inductor, so that the current will increase. So in that case, the current that is already flowing is represented by the I naught 0 plus. and when the current is increasing, then there will be some transient condition, so there will be gradual increase in the current. Then after that it will either settle at a higher value or it will go on increasing depending on the applied current source. I hope you understood what is meant by the initial condition. Okay. Any doubts till now? If you have any doubts, you can ask. I hope everyone is able to unmute and talk. Okay. So this is a table that I wanted to tell you. So okay, so we have already discussed the first Laplacian transform, that is the unit step function. So if it f of t is equal to 1 or u of t, then the Laplace transform is f of s is equal to 1 by s. Similarly, we can have the Laplace transform of delta of t, which is delta is t. What is it called? It is called the unit impulse function, which is given by L of delta of t is equal to 1. Okay. Similarly, the Laplace transform of a ramp signal, which is given by t is equal to 1 by s square, and the general expression is L of t power n is given by n factorial by s raised to n plus 1. Okay. So, for example, let us take this case. So, actually, we are having t raised to 1. So, that will be equal to 1 factorial divided by s raised to 1 plus 1. So, that is how we got as it is equal to 1 by s square. So, the Laplace transform of t is 1 by s square. Similarly, you can find Laplace transform of t square, which is given by 2 factorial divided by s raised to 2 plus 1, which is equal to 2 by s raised to 3. Similarly, you can find the Laplacian transform of t power n, which is given by this equation. L of t power n is equal to n factorial divided by s raised to n plus 1. So whenever you encounter a time function raised of the form t raised to a constant value, you can use this expression to convert it to the Laplacian domain. Another function which we have already discussed is L of e power minus at is equal to 1 by s plus a, which we have already written. And another expression is L of t into e power minus at is equal to 1 by s plus a the whole square. Actually, a property of the Laplace transform, which is written as L of t power n into x of t is equal to minus 1 raised to n d raised to n by ds raised to n into x of s. So how to interpret this property is, so let us take this previous example where we were having f of t is equal to e power minus at. So instead of f of t, let me write it as equal to x of t. So that is equal to e power minus at. Now what is x of s of this? So that is already given here. X of s is of it is the Laplace transform of e power minus at, which is equal to 1 by s plus a. Okay. Now I want to find the Laplace transform of say x of t is equal to t into e power minus at. So what I should do is it will be given by minus 1 raised to, so here t is equal to t raised to 1, right? So I have to do minus 1 raised to 1 d by ds of xs. So what is xs? Xs is already equal to 1 by s plus a. So I will have minus 1 raised to 1 is equal to minus 1 into derivative of d by ds of 1 by s plus a. So that is equal to minus 1 into minus 1 by s plus a the whole square, right? So that will be equal to 1 by s plus a the whole square. So I can do this transformation using this identity. Similarly, I want to go for a different function. For example, x of t is equal to t square e power minus at. So by using this property that is written in the blue color here, so you can find out what is the Laplace transform of t square e power minus at. So that will turn out to be minus 1 raised to 2 t square by ds square into x of s. So here x of s is 1 by s plus a, right? That is the Laplacian transform of this quantity e power minus at. So to that only we are multiplying this t square quantity. So that will be equal to 1 into the derivative of d by ds of, and what is derivative of 1 by s plus a, that we have already written here, which is equal to minus 1 by s plus a the whole square. So you have to find the derivative of this. So that will turn out to be equal to 2 by s plus a the whole cube. See, it's very easy, right? So once you know the Laplace transform of certain standard quantities, then you can find out the Laplace transform using this property. Okay. So any doubt in this explanation? How you can use these properties of Laplace transform? Okay. Now moving on, another important function that we have already seen is the sine omega t function, which we have already said. Laplace transform of sine omega t is omega by s square plus omega square. Similarly, Laplace transform of cos omega t is s by s square plus omega square. So these table you have to learn by heart. Okay, then only you'll be able to apply the Laplace transform methods to solve the network analysis problems. So certain standard Laplacian transforms you have to learn by heart. Okay, just like in your multiplication table, you have to learn by heart these transformations. Also, certain important properties like this, like L of t raised to n and L of t raised to n into x of n, like that, x of t, like that. Now moving on, another property that I would like to tell is, we already know what is the Laplace transform of sine omega t. So what happens when we multiply the sine omega t with e power minus at, right? So this is the property that we can use. So when we have a function x of t, and you who is having a Laplacian transform of x of s, then you multiply this time quantity function x of t with e power say s naught into t, then the Laplacian transform is nothing but x of s minus s naught, where s naught is a complex constant, like we are already familiar with. That is the exponential function. I already told that e power s into t is the exponential function where s is a complex constant. Okay. For example, let us take this sine omega t case. So here in this case, we are having s of t is equal to sine omega t, and for which we already know what is the Laplace transform, which is Laplace transform of sine omega t, which we are familiar with. It is equal to omega by s square plus omega square. Okay. Now, what is the Laplace transform when of sine omega t, which is multiplied with e power minus et? So our new function is x of t is equal to e power minus at sine omega t. You only have to do, we only have to subtract this, instead of s, just replace. So this is, okay. Therefore, Laplace transform of e power minus at sine omega t is equal to omega by s square plus omega square, and just replace s with, where s is to be replaced with, s is to be replaced with s minus minus a, right? Okay, so that we will have it is equal to omega by s plus a the whole square plus omega square. So remember, when we are having uh, e power minus 80. So here in this, what do you call, in this property, I have written as it is equal to e power s naught into t. So you have to do s minus s naught. So in this example, we are taking it as equal to e power minus 80. So whatever this s naught is now become equal to minus a. So in our property, it is written as replace s with s minus s naught. So retain the sign so that we will have the Laplace transform of any quantity, that is L of e power minus 80 into sine omega t is equal to omega by s square, s plus a the whole square plus omega square. Hope you understood what is done here. If you have understood, then tell me what is the Laplace transform of this function. That is 3 e power 2t into ut. So if you try to do the integral, then it will be very complicated because you have to do integration by parts and etc. A similar function. Okay, here it is likely it is a unit step function, so it's very simple. So what should we do? Consider this function as product of two functions. So let us take this as the this unit step function as the function to which a function exponential function e power 2t is multiplied with. So you already know what is the Laplace transform of u of t. So Laplace transform of u of t is equal to 1 by s, right? Now to this, you are going to multiply e power 2t. So what happens to this? So that is equal to 1 by s plus a. Just replace s with s a is equal to 2. Okay. So the answer is 1 by s minus 2. Okay. But here we have x of t is equal to 3 e power 2t into u of t. So the given question is x of t is equal to 3 e power 2t into u of t. So what is x of s? X of s is equal to 3 by s minus 2. Hope you understood how it is done. Using the property of Laplace transform, we have done this without doing any integration. Okay. Any doubt? You can interrupt me. If you are not interrupting, I am assuming that you are following. Okay. So we have already seen what is the derivative of Laplace transform of the derivative of a function, which is given by s into f of s minus the initial condition f of 0 plus. Okay. So in short, if you have derivative of higher orders, for example, Laplace transform of d square f by dt square is equal to s square into f of s minus s into f naught minus f dash of 0, where f dash of 0 is the time derivative, the first derivative of f of 0 with with respect to time. Similarly, if you are having higher order derivatives, you can use this general formula, the property of Laplace transform, which you can use. So Laplace transform of the nth derivative of f of t of any function in time domain is given by s raised to n into f of s minus s raised to n minus 1 f of 0 minus s raised to n minus 2, the first derivative of f of 0, etc., minus last in the end you will have the n minus 1 the derivative of f of 0. Okay. So you can use that relationship to find the Laplace transform of the derivative of a function. Similarly, you have a ready formula available to find out the Laplace transform of the integral of a function. So integral 0 to t f of tau d tau is equal to f of s by s. So the method to remember is, for derivative you have to multiply s with f of s, and for integral you have to divide s by uh, from f of s. Okay. Another property of Laplace transform that is called the time shifting. So when you have a function which is time shifted, so f of Laplace transform of f of t minus t1, when you're doing time shifting, so this is time shifting, then in the frequency domain you have to multiply it with e power minus t1 s with a Laplace transform of the original function. Okay, for example, I can tell you, you already know what is the Laplace transform of u of t. So the Laplace transform of u of t is equal to 1 by s. Okay. Now I want to find what is the Laplace transform of u of t minus 2. It is time shifted, right? It is delayed by 2 seconds. That is right shifted. So what should I do? I have to only multiply with e power minus 2s into 1 by s. So just multiply it with e power minus 2s. So this is the property that you can use, because you already know what is the Laplace transform of u of t, which is equal to 1 by s. So you'll be able to deduce what is the Laplace transform of u of t minus 2, that is time shifted. So when you come to the frequency domain, you have to only multiply it with e power minus 2s and the transformation of the original function. So this way you will be able to find out the Laplace transform of most common functions that we may encounter in our network analysis course. Sometimes we may not encounter functions that are very similar to these things that we have already discussed. So we may have some higher order polynomials coming in our equation. So the mathematical tool that, or mathematical trick that we are going to rely on, is called partial fraction expansions. So whenever you have higher degree polynomials as our equations, in order to convert it back to the inverse Laplacian transform, then we can use this partial fraction expansions. So what we are trying to do is, in partial fraction expansion, we are trying to break down this complicated function into a sum of simpler rational fractions. They are called, otherwise called as the principal parts, and each pole will contribute to a principal part. So that I will try to explain. I hope you know what is pole and zero. So in briefly, I will tell you what is a zero. Zero is that particular values of s, or the roots of this polynomial r of s, which is going to bring this value of this function to equal to zero. So they are called zeros of this polynomial, and poles of this polynomial are those roots of s, which is going to bring the value of this polynomial to infinity. So if you are not able to understand what it is, just leave it. You will be able to understand it once you undergo course in control system. So in short, in general, we can have when we encounter polynomials, we can either have polynomials in which we have simple poles. So it will have functions like s minus a in the denominator polynomial. Okay. So when such cases are coming, so when we will do certain examples, you will be able to understand this. Then how we can find it. So I told, like, we can represent a polynomial, say r of s, which is given by p of s divided by q of s. So in partial fraction form, we divide this to certain sum of uh, certain principal elements, okay, which we the term that we use. So we can have this is equal to a1 divided by s minus a1 plus a2 divided by s minus a2. Like that we can have we can express this in terms of the sum of the um, principal elements, okay. So in this case, this is an example of a simple pole in which we do not have repetitions of this s minus a. Whereas if you are having something like s minus a1 the whole square, then it is called they are called double poles. Okay, so that's the difference between simple pole and a double pole. So if this is the case, then how can we evaluate this constant that is a1? So we can evaluate this constant by using this identity. So this a could be found out by limiting s tending to a, multiply this polynomial r of s that we are taking, multiply that polynomial with s minus a, and then take the limit as s tends to a. So the second point is telling that if A is complex, so here A is complex, then A star is also a simple pole. An example I can give you is, for example, let us have the polynomial that we are having is equal to 1 by s square minus 1. Let us consider such a polynomial. So how can I express this as a partial fraction? So I can split this as equal to a1 by s minus 1, sorry, s minus j plus a2 by, first of all, I will tell you how I can write like this. So if you observe this, I have to write it in this particular form, like s minus a, s minus b, like that. Okay. So what is s square minus 1? So that is equal to s minus j into s plus j, right? So now I can use the partial fraction technique to write it as equal to a1 by s minus j plus a2 by s minus, sorry, s plus j. Okay, now my next aim is to find out what is a1 and a2, these constants. So before that, I will try to explain what is written here. For example, if this a, that is whatever we are having in the denominator, this pole is a complex quantity. For example, j is a complex number, right? Then I can have the conjugate, complex conjugate of j also as a simple pole. So the complex conjugate of plus j is nothing but minus j, right? So that is why I can split it as equal to a1 by s minus j plus a2 by s plus j. Or always we can say that whenever you have complex poles, they always appear in conjugate pairs. Similarly, when you are having a complex quantity, a complex pole in the denominator, that is, you are having a complex pole, then the um, numerator of the principal part, that is our a, is will also be a complex, and it will also be in its complex conjugates. So the meaning is that, so what if I try to find out in this example, I am trying to find out what is a1 and a2. So what is a1? I can use this equation, right? I can use this equation to find out what is a1 here. So let me write a1 is equal to limit s tending to j s minus j into this r of s, right? So that is 1 divided by s minus j into s plus j. So what is this? So you have to just replace s with j here. So this will come out to be equal to 1 by 2j. So 1 by 2 is zero point 0.5 and 1 by j is minus j. So we'll have minus zero point 0.5 j as the answer. So if you have a1 is equal to minus zero point 0.5 j, then a2 will be equal to a1 conjugate. So that is what is written here. So it means that the conjugate of complex conjugate of minus 0.5j, which is equal to 0.5j, will be also the constant that we want to find out. I hope all this will be covered in your mathematical course. And the third property told here is, if a is equal to 0, so then a is the final value of r of t. So it means that, for example, instead of let us take a new function, say r of s is equal to 1 by s into s minus a. So if you consider this first s, here we do not have any term which is subtracted from here. So here, the value of the pole here is equal to 0. Okay. So in such a case, I apply the partial fraction equation. So I split this as a1 by s plus a2 by s minus a. Now I take the Laplace inform of this, inverse Laplace transform of this. Then I will have, so what is the inverse Laplace transform? It will be a1 into u of t, because you already know that u of inverse of, Laplace transform of u of t is equal to 1 by s. So I can write it as a1 into u of t plus a2 into e power 80, right? Sorry, small a. Okay. So this will be the initial condition. So what it means is that, this will be the final value of RT. So what it means is that I limit t tends to infinity. So what is the meaning of final value? It means that as time tends to infinity, what will be the value of the function? So that is called the final value of this function, right? So as limit t tends to infinity, r of t, what is it going to happen? So in the time domain, you have to use the smaller case. Okay. In the frequency domain, you have to use the uppercase. So as t tends to infinity, r of t, what will it will be? So here you will have e power. I'm going to slightly modify this function because otherwise it will go to infinity. Okay. So let me write this as equal to s plus a. So this will be s plus a. So you will have e power minus at. Okay. So that you will be able to understand this. Otherwise, the final value will be infinity. Okay. So what will happen? So this will be equal to a1 into u of infinity. So that is nothing but a1. The second portion will tend to 0, right? So because it will be equal to a2 divided by e power infinity, it will go. So this quantity is infinity, so that the overall quantity will be equal to 0. So this term will vanish to be equal to 0, and we will have only a1. So that is the point that is explained here. So whenever you have whenever you see that in your expression you are having a pole, one of the pole is equal to 0, then the principal part of that quantity, that partial principal part of that, or the constant part of that principal uh, value will be equal to the constant of that principal part will be its final value. So that is the point mentioned here. And the second case that we can encounter is when we have repeated poles, or it is otherwise called the double pole. An example is given here. When we have r of s is having s minus b the whole square repeated like that. Okay. Then we have to, in order to use the partial fraction expression, we have to split that into partial fraction like this. Okay, so we have to split it like this. And in order to evaluate the values of the constants v1 and v2, we have to rely on these equations. So first we have to find out the uh, constant of the principal part which is having the higher degree. For example, there are two principal parts. So the first principal part is b1 by s minus b. The second principal part is b2 by s minus b the whole square. So the principal part having the higher degree in the denominator is s minus b the whole square. So you have to find out b2 first using this equation. So this equation is similar to the equation that we have used to find the a1 equation, which is limit s tending to a s minus a into r of s. So just multiply this s minus b the whole square to the original polynomial and limit s tending to p. So once you have this b2 evaluated, in order to find b1, just subtract this principal part containing the constant b2 from the original function r of s, and then multiply it with s minus b. That is the denominator of the first principal part, and then limit s tends to b. So this is the trick that we can use to find out the constants of the partial fraction. So when we do certain numerical problem, you will be able to understand what I was trying to tell you. And the similar cases apply. For example, if b is a complex quantity which is happening in the double pole, then b conjugate, the complex conjugate of b will also be a pole for this function. Okay, so we'll do start with certain examples. Any doubts so far in the text or any of the slides? Then you can ask me. Otherwise, you can start working out this problem. Okay, no doubts. Then I got disconnected. Okay. Okay, so I hope now it is rectified. Okay, so here let us write our function r of s is equal to 1 by s into s minus a, sorry, a square minus a square. Okay, so this could be written as 1 by s into s plus a into s minus a. Now let us apply the partial fraction approximations, partial fraction technique here. So this could be split as the sum of three principal parts. Why three principal parts? Because there are three poles that are going to contribute to this polynomial. So the poles are s is equal to 0, s is equal to minus a, and s is equal to a. So we can write this as equal to a by s plus b by s plus a plus c by s minus a. Okay. So once you write this, then you can evaluate what are these quantities a, b, and c. So this method we have already studied. So in order to find a, multiply this polynomial r of s. So what is a? A is equal to limit s tending to 0 into s into r of s. Okay. So that will be, similarly you can evaluate what is b, which is equal to limit s tending to minus a, s plus a into r of s, and c is equal to limit s tending to a, s minus a into r of s. Oh, sorry, I was not audible. Any doubts in that? Actually, because no, I am using sharing the screen. I will not know whether any my audio is coming or not. So I think anybody can unmute and say. Now only I saw the message that my audio is not coming. Any doubts in the steps? I have written all the steps here.
No, sir.
Okay. So I will quickly tell because my connection got dropped here. So RFS, I have written the partial fraction like this, split it up like that. Then we this identity we have already discussed because this is a symbol pole. S plus A is a symbol pole, so I can find out what is the S as well as S plus A is a symbol pole. So I can use this identity, just limit S tend to 0, S into RFS, so that I can evaluate the constants A, B, and C. Similarly, you can evaluate what are the constants B and C. So once I have all the constant parts of the principal parts, so these are the constants and these are the principal parts. And why I wrote like this as because of the contribution of these poles. So we have three poles here. S is equal to 0 is a pole, S is equal to minus A is a pole, and S is equal to A is another pole. So we have three poles. So we can have three principal parts. So that is why I split into three parts. Okay, then use the identity to find out what are the constants of these principal parts A, B, and C. So this identity is familiar to us. So otherwise memorize it or memorize the method it is applied. So once you apply and find out all the constants, then you apply back all the constants to these portions A, B, and C, so that you will have RFS, the our polynomial to of which we have to find the inverse Laplace transform. Then once you write like this, we already know that the Laplace transform of U of t is equal to 1 by s, or the Laplace transform of 1 is equal to 1 by s, so that the inverse Laplace of 1 by s is U of t, or is equal to 1. Then you have to use the linearity property of the uh, inverse Laplace transform. You can retain this constant using the linearity. You are multiplying it, then just retain it 1 by a square, and you can either write it as u of t or equal to 1. Okay, it is up to you. Then already for the second part, you already know what is the Laplace transform of e power minus at, that is equal to 1 by s plus a. So you can write that the inverse Laplace transform of 1 by s plus a is e power minus at, then apply to the second part. Okay, again use the linearity property of inverse Laplace transform. You can retain the constants, that is 1 by 2a square, and in the second principal part and the third principal part. Okay, so you have 1 by 2a square into e power minus at plus 1 by 2a square into e power minus at. Then you, when you take 1 by a square common outside, you will have e power at plus e power minus at. So you must be familiar with the hyperbolic identities, that is cosh, and I have written sin h function also for your reference. So cosh of x could be written as e power x plus e power minus x the whole divided by 2. Here x is to be replaced with 80. So what we are having here is nothing but our cosh 80. And for depending on the options in gate, maybe there will be, it will be an objective type, there will be multiple choices. So you can simplify it to one of the option that could be available. For example, you may see an option like this, then you have to click. So sometimes you may get stuck here and you are not seeing any answer, any possible answer. Don't stop there, apply the identity and simplify this. So this is how you can apply the concepts of partial derivatives to find out the inverse Laplace transform. So this was the example for symbol poles. We will do another example in which double poles are coming. So find the time domain current I of t if the Laplace transform is like this. So in this question, the Laplace transform is already given, but when we do the do the network problems, or when we try to solve the network equations, we have to write this Laplace transform of the currents. So that we'll see in the coming time. So here I can write I of s is equal to Here I can write I of s is equal to s minus 10 divided by s square into s square plus 1. Okay, I can also write it more simpler manner. So actually this is a complex pole here sitting here. So it is consisting of two poles here. So I have to split it further so that I will have the required number of principal parts. So numerator will be written as such, and the denominator will have a square. Here there is only one pole, that is s is equal to 0. And here I have two poles. So one is contributed by s is equal to j, which is written by s minus j, and the other one is contributed by s is equal to minus j, which is written as s plus j. Okay. Now I can use the partial fraction. So okay, so this is written as equal to a by s minus j plus a conjugate by s plus j, because this pole is a complex pole. So you know that the constants of this principal part is going to be appearing as complex conjugates. It is represented by a star, and the contribution by this repeated pole at 0 will be written as equal to b1 by s plus b2 by s square. Okay. Now use your limits thing to find out, to evaluate each of these values. How can you find out what is a? A is equal to limit s tends to j into j into j into s minus j into I of s. Okay. Similarly, once you have a, then b is a conjugate is, you can write, which is the complex conjugate of a. Then, so should we evaluate b1 first or b2 first? Yes, we have to evaluate b2 first. So what is the equation for b2? b2 is limit s tends to 0 square into I of s. So once you have b2, then we can evaluate what is b1. Just again, limit s tends to 0 s into I of s minus b2 by s square. So one thing I will show you how you can do. So this is when s minus 10 divided by, when you multiply it with s minus j, s minus j will vanish. So we will have s square into s plus j and replace s with j. Okay, s tending to j. So we will have j in the numerator minus j minus 10 divided by, we will have j square here, which is equal to minus 1, and replace this with j plus j, so it will be 2j. Okay, so we have in the numerator j plus 10, this j square is minus 1, right? So that is equal to minus 1, and here we have 2j. Now bring this to the numerator, so this j will get cancelled, so it will be equal to 0.5 plus, and 10 by j is, sorry, 10 by 2 is equal to 5, and 1 by j is minus j. So we'll have one minus sign here, minus g5. So that is the constant for the first principal part, that is a by s minus j. Here it should be plus, right? So it will be minus j. So it will be minus 0.5 minus j5. Okay. So once you have a, then a conjugate will be equal to minus 0.5 plus j5. Okay. So that will be there. Similarly, you can evaluate what is b2. Are you getting b2? Okay, I will give out the answer. So just check whether you are getting that or not. So if you are not getting this, give me tell me in the next class. I will try to do it for you. So b2 you should get it as equal to minus 10, and b1 you should get it as equal to 1. So once you have these constants evaluated, now you can write the polynomial in S as the sum of the principal parts, as a is equal to minus 0.5 minus j5 divided by s minus j plus minus 0.5 plus j5 divided by s plus g minus, sorry, plus 1 divided by s minus 10 divided by s square. Okay. So once you write our polynomial in S domain, then you can find what is the, convert it to the time domain by taking the Laplace inverse. So this is of the form 1 divided by s minus a form. So the Laplace inverse of 1 divided by uh, s minus a is equal to e power at, right? So you can retain the numerator as such because it's a constant, and to that you have to multiply e power, instead of a it will be j, and we have t coming. Okay. Plus minus 0.5 plus j5 e power minus gt plus 1 by s. You can write it as either 1 or u of t, and 10 by s square, it is 10 into t, because you know the Laplace transform of uh, t is 1 by s square. So the Laplace inverse of 1 by s square is t. So these are the Laplacian identities that we are used to find out the inverse Laplace transform of this polynomial. Okay, you can rearrange this and make it more beautiful. I am leaving it there. Any doubts? A similar problem. Here we can write this as equal to s plus 1 divided by s into s plus 2 the whole square. Okay, so this is an example for repeated pole, and here we are having a simple pole here. Okay, so s is equal to 0 is a simple pole, and s is equal to minus 2 is repeated here. So again use that identity of partial derivatives, that so that we can simplify this. So I can write this as equal to a divided by s plus b1 by s plus 2 plus b2 by s plus 2 the whole square. Now I can evaluate what is a. A is equal to limit s tending to 0 s into, let me call this as r of s. Okay, so this is r of s is equal to, for the convenience, so what is a is equal to s into limit s tends to 0 of s into r of s. So that is equal to s plus 1 divided by s plus 2 the whole square as s tends to 0. So that will be 0 plus 1 divided by 0 plus 2 the whole square, that is equal to 1 by 4. Similarly, you can evaluate what is b1 and b2. So first you have to evaluate b2, right? B2 you can evaluate, and after that you can evaluate what is b1. So b2, just verify whether you're getting s equal to 1 by 2. Who is that? Nisha Kaseva. So if you are getting b2 like this, then you can evaluate what is b1. This is equal to minus 1 by 4. So tell me the Laplace inverse. Now I can write r of s is equal to 1 by 4 divided by s plus 1 by 2 divided by s plus 2 minus 1 by 4 divided by s plus 2 the whole square. So what is r of t? So this will be 1 by 4 and this will be 1 by 2 e power minus 2t. What about this? Which property you can use? You know that L of t is equal to 1 by h square. So what is L of e power minus 2t into t? So I said just replace s with s plus 2, right?
Plus 2.
Okay. So that it will be 1 by s plus 2 the whole square. So what is the Laplace inverse of 1 by s plus 2 the whole square? It is e power minus 2t into t. So that property of inverse Laplace transform you can use here. You don't have to do any integration here. So that will be 1 by 4 into t e power minus 2t. Now is the application of this in our circuit analysis. From here onwards, we are going to deal with our network circuits. So for that, these were the base, mathematical base, or those who have already studied, it was a refresher or revision. Now we are going to deal with the resistors, inductors, and capacitors. So how, assume that there is a current I flowing through the resistor R. So when we convert this to the Laplacian or the S domain, the current becomes I of S. So what is the voltage across this resistor? So here the driving quantity is the I, and the required quantity is the voltage across the resistor. So we are trying to find out what is the voltage across the resistor. So in time domain, I can write the voltage across the resistor. So VR of t, we already know V is equal to the product of current into the resistance value. So V is equal to IR. So IT into I of t into R. Now what? How can we convert this to the S domain? So take the Laplace inverse on both the sides. So we can write the S domain voltage VR of S. So see, I have written this in the capital letter because now it is in the complex frequency domain. So that is equal to I of S into R. So VR of S is equal to I of S into R. Another quantity that we see is an inductor. So there are two cases. In the first case, so this is case 1, in which we have I of 0 plus, that is the initial current that is flowing in the direction left to right. So we are taking the current I of t flowing in this direction, and initially a current was already there in the inductor, which is from left to right itself. So both these currents are in the same direction. Okay. So how can I write the time domain equation here? Here I will prove that this is a mistake here. Actually, it should be minus here. So in the time domain, I can write the voltage across the inductor VL of t is equal to L di by dt, right? L into dit by dt, d by dt of I of t. Okay. Now I convert this to the Laplacian domain. So I can write this is equal to VL of S. So that will be equal to L. And what is the Laplace transform of the derivative of a function? So that is, if you remember, where we have written the Laplace transform of the derivative L of d by dt of f of t, it was written as equal to s into f of s minus f of 0 plus. So I am going to take, sorry, there is no L here. Okay, this is the identity that should be L of. Okay. So this is the identity that we are going to apply here. So this L is not the inductor value. This is the Laplace operation. Okay, this is the Laplace operator. Okay. L of df d by dt of f of t is equal to s into f of s minus f of 0 plus. This is the inductor value L. Okay, don't get confused. So Laplace transform of d by dt of I of t is equal to s into I of s minus some initial current that was flowing. So that is some initial current. So which initial current was flowing here? This current was flowing. Okay, and now we are going to take the voltage from here, right? So how can a voltage source, if you replace with a voltage source, how can that current be driven in that direction? So we have to put a voltage source in this manner, like with polarity like this. Now if I write the voltage equation, so I am trying to see what is the I am going to write the Kirchhoff's current voltage law here. Okay, I am going to measure this. So what is V of S? I am going to traverse this loop in this manner, right? So there will be some drop here, plus minus drop here. So that will be taken as plus. But here I am having a voltage rise. So that will be taken as minus. Okay. So okay. So that will be equal to okay. So there's no mistake here then. So that will be taken as minus of minus I naught plus. Okay. So that will be equal to S into L into I of S plus I of 0 plus. Sorry, L is also there. L into I of 0 plus. So that is how we have replaced this with this particular model. Okay, so we can replace an inductor in the time domain with an inductor which is multiplied with S into L and a voltage source with polarity which is driving the current, the initial current in the same direction, that is minus to plus. So that will be L into I of 0. So that the voltage could be written as S into Li of S plus L into I of 0 plus. Okay, so this is the proof for that. Now considering the case B, so this is A. Case B, here we are having the initial current from right to left. Okay, assuming that the initial current was flowing in this opposite direction, and now we are going to set up a current in the rightward direction. So this is the I of t. A new current is established like this. So in order to model this initial current, we have replaced it with a voltage source with polarity such that it is going to drive the current in the leftward manner. So plus is on the left and minus is on the right hand side. Now I try to find out what is the voltage across this inductor. The similar manner we have done earlier. Now I have to traverse it like this. Okay. So there is a voltage drop here and there is another voltage drop here. So let me first write the equation for the voltage across the inductor in the time domain. We know that V L of t is equal to L into dit by dt. Now I have to convert to the Laplacian domain, then take the Laplace inverse on the left hand side as well as the right hand side. So on the right hand side, I have inductance value L and the Laplace inverse, sorry, Laplace transform of di by dt. So that is again S into I of S minus the initial current. Okay. So what is the initial current here? So now I am traversing in this manner, right? So it will have the same quantity, right? So it will be plus 2 minus. So that will be equal to S into AFS minus I naught. Okay, now it is in the opposite manner. So it will be taken as plus itself. Okay, so that will be equal to I naught plus. So we are getting a minus sign here. Okay. Okay, we'll take one example and we'll see. Actually, there should be a minus sign here, and it is correct only. So we'll see when we take one example problem in the future. So now taking the capacitor, we are considering that there is an initial charge across this capacitor with polarity like this, plus on the left hand side and minus on the right hand side. And now we are going to drive a current I through this capacitor. Okay. Now it is modeled like we are having a capacitor already, and in order to represent this, we have to use integral IC of t dt. Okay, where I have a current that is going to flow, that is flowing through the capacitor. Plus, there is one initial voltage that is available with polarity like this. Okay, now we are traversing from this left to right. Okay, so we are encountering the polarity from plus to minus. So this voltage is in additive manner. So this is plus V naught. Okay, so that should be taken as equal to plus V naught. Now, how can we express this? This is case number A. How can we express this voltage in the Laplacian domain? So that is Vc of S, which is equal to 1 by C, and the Laplace uh, transform of integral is I of S divided by S. Okay, and for V naught, it will be V naught by S. So that will take us to the result that is written here. So we have the voltage across the uh, capacitor in the S domain will be equal to I of S divided by S into C plus V naught divided by S. Now taking in the case B, this is the second case in which we have the capacitor charged with the polarity opposite to the previous case. So we have polarity uh, with polarities mark minus on the left hand side and plus on the right hand side. So this will could be modeled with this circuit. We have a capacitor with a constant voltage source with polarity mark like this. So this is the initial charge, that is V of 0 plus. Okay. Now if I write the voltage equation across the capacitor in the time domain, I can write using the same expression Vc of t is equal to 1 by C integral ICT dt. But here the polarity of the voltage is opposites. Opposite means opposite to the direction in which we are traversing. We are traversing from left to right manner. So we have what it is equal to minus of V naught. So that will be equal to, now I take the Laplace transform Vc of S, that will be equal to 1 by C, and Laplace transform of integral is I of S divided by S minus V naught divided by S. Okay. So this is the uh, voltage equation in the Laplacian domain. So that is a proof for this. Okay, how you can replace a capacitor with its equivalent in the Laplacian domain. So any doubt till now? Okay. So if it is clear, this is a summary of that. So when we do this numerical problem, we will be able to sort out the problem with the inductor. Okay. So this is the example in which a series RL circuit is there. The values are also given R and L. And at t is equal to 0, when the current in the circuit is 2 ampere. So at the 0th instant, there is a current flowing through the inductor. Okay. At that instant, a source of 50 volt is applied. So we have to find out what is the current. Okay. What is the new current? Okay, so we will find out what is the voltage across this inductor. Okay. So initially there is an current that is flowing through this inductor. So that is given, that could be modeled as equal to 2 into u of minus t. What is u of minus t? You already know what is u of t. That is equal to um, this. It will have the shape like this. So this is our u of t. U of t. So this is having a value 1. So that you can have what is u of minus t. So I told you can invert it like this. So this is u of minus t. Okay, it is just in mirror image of that. So this is u of minus t. Okay. So this is going to represent what is happening. So how is u of t defined? U of t is defined 0 for t less than 0, and it is defined as equal to 1 for t greater than 0. This is how we have defined it. Okay. So but we need to represent the initial condition. So that is why we are taking the mirror of this with respect to the time, and it is multiplied with 2. So this could be replaced, this sentence, that is there is an initial current of 2 ampere, could be replaced with a constant current source which is having the value 2 into u of minus t. Okay. So that is representing the I naught. So this is our I naught value. Okay. I of 0 plus in the time domain. At that instant, we are applying a voltage at t is equal to 0, having a magnitude equal to 50 volt. Now we have to draw what is the uh, circuit in the Laplacian domain. How can we draw the circuit in the Laplacian domain? So we have already seen how we can replace a resistor. A resistor could be replaced. So we have a voltage source plus minus, and we have the resistor and this inductor. So how should I mark the polarity of the voltage? Initially this current was flowing in this manner. Okay. So when I transform it to the S domain, I have to replace it with the voltage source which is taking the current the same direction as the initial current. Okay. So this is how I will draw. This is our voltage source which is attached at uh, t is equal to 0. Okay. Now I have to write these values. So how can I write R? R is to be replaced with R only. Okay. So that we have seen here. So for resistor, we have to replace it with R itself. And for inductor, the current is in the same direction as that of the applied current. Then polarity is marked in that manner itself. And inductance value S is L is replaced with S into L. And the voltage is written as L into I naught plus. Sorry. So this is to be replaced with S into L, and this is to be replaced with S into L, and this is to be replaced with L into I of 0 plus. And what about this voltage? So we are having the V of t is equal to 50 into U of t. So we can write V of S is equal to 50 divided by S. So once this is converted to the circuit in the Laplace domain, then we can find out what is the current which is flowing through the circuit. So initially this current was that is flowing is actually I of t. So this I is I of t. Now you need to find out what is I of S only. Okay. So this is actually I of t. Okay. Now this is transformed to I of S. Now if you want to write the KVL equation for this loop, I can write the KVL equation. So I can write 50 divided by S is equal to R into I of S plus SL into IFS. And now I am traversing from, so this is a, when IFS is flowing, there is a voltage drop here and there is one voltage drop here. So I got all this plus. And here I can see that it's a voltage rise is happening. So this should be replaced with minus L into I of 0 plus. So we got the answer whether it is minus or plus. So when this is happening, it should be actually minus here. Okay, so this should be equal to minus here. So there's a mistake here. So correct in the inductor value. So if it is happening in the same direction, then it should be equal to minus here. Okay. So we were traversing in the same direction. So the current, the direction which we are traversing in this manner, and this current is also in the same direction. So no need of taking it in the opposite manner. So this is plus itself. Okay. So that will be, so this has to be replaced with minus. Okay. Okay. In the next class, probably I can explain you more. So this is how you can write the Kirchhoff's voltage law in the S domain. So once you write this equation like this, then you can find out what is I of S. So I of S could be taken out from here. So that will be equal to 50 divided by S, 50 divided by S, divided by R plus SL, fifty divided by S plus L into I of 0 divided by R plus SL. Okay. So you will be given what is the value of the inductor here, L value, and we have already have what is the value of I naught. Then you can substitute those values and you simplify this and bring it to the form, and then use the partial fraction expansion so that you can find out what is the inverse Laplace transform. Okay. So bringing S to the denominator, or you can divide this with L also. Okay, so I will see one example on how to do the inverse Laplace transform. So before, so can you find out what is I of S here? So substitute the values. L is equal to 2.5 millihenry, and I naught is given as equal to 2 ampere, and R is given as 5 ohm here. So this is 5 ohm. Now how can I simplify this? So we can write this equal to S into I naught plus 50 divided by L divided by S into S plus R by L. I am trying to write it in the form S plus something. Okay. Especially in the denominator, I have to write it of the forms S into S plus something, so that I can use the partial fraction expansion here. So this is multiplied with here and dividing with L throughout. The numerator and denominator you have to divide with throughout by L, so that we will have S here. So here will be R by L, and taking that L common out, so L is cancelled here and then multiplied with S, so S into I naught, and this is also divided with L, so we have 50 divided by L. So this is the rearranged value. If you want, you can bring this I naught also to the to this, but no need. Okay, retain it as such, because numerator doesn't matter in the partial fraction expansion. So this is equal to 2s plus and 50 divided by 2.5 into 10 power minus 3. 50 divided by 2.5. So that is 20 into 10 power 3, right? Divided by S into S plus R by L. Okay, so here we have R is equal to 5 ohm, so that will be 5 divided by L is equal to 2.5 millihenry, so that is 50 by 2.5, 50 by 25, that is 2. So that will be 2 into 10 power 3. Okay, now you can use this partial fraction, so that will be written as equal to A by S plus B divided by S plus 2000. Use the identity. What is A? A is equal to limit S tends to 0 of 2s plus 20 into 10 power 3 divided by S plus 2000. So that will be equal to 20 into 10 power 3 divided by 2000. So that will be equal to 10. How can we evaluate B? B is equal to limit S tends to minus 2000 into 2s plus 20 into 10 power 3 divided by S. So that will be equal to how much you are getting? So that will be 2 into minus 2000, right? Minus 2 into 10 power. I will write it as minus 2000. Sorry. Plus 20 into 10 power 3 divided by minus 2000. So we have 3's cut here. is minus 4 plus 20, 16. 16 divided by minus 2 is minus 8. Now I can write the current I of S is equal to 10 divided by S minus 8 divided by S plus 2000. So what is I of t? It will be equal to 10 into U of t. Or I can simply put a 10 also. Okay, don't worry. Minus 8 into. So this is of the form 1 by S plus A. So the Laplace inverse of 1 by S plus A is e power minus 80. Okay, so here I am having 1 by S plus 2000. So the inverse Laplace transform is e power minus 2000 t. So this is the current that is going to flow through that combination of inductor and resistor. Are you following? Are you getting this answer? Okay, if you are getting, let's try. If you are not getting, we will pause here. So I hope you must have understood. You have got a flavor of Laplace transform. How we can analyze, you apply it in our circuit analysis. So how to so today we have seen how we can represent a circuit in time domain in the S domain, complex frequency domain, that is S domain, and how we can analyze that by finding out what is the current unknown quantity or voltage. So before next class tomorrow, take a look at the inductor also. So whether any mistake is done while we are trying to model this, I will also come up with the correct result, whether it is correct or wrong. Because you also think from your end, you refer some textbooks, study this. If you are having any doubts in the partial fraction or finding out the Laplace transform, inverse Laplace transform, you can ask me. Okay, so we'll stop for now. So the next class is tomorrow at 6 o'clock. So see you all then.